Good afternoon, everybody. I'm just going to wait just maybe another sort of 30 seconds or so, just because I can see people joining the presentation. And really just wanted to start by saying a warm welcome to you all, and thank you for joining us this afternoon. So the presentation this afternoon is going to be about ArcelorMittal's response to the climate emergency. Obviously, the climate emergency is it's a global issue, and we all have a part to play in it. And I know as an organisation we're very keen to play a part in that. Just by way of introduction to myself, my name is Walter Swann. I'm a Steligence construction engineer for ArcelorMittal in the UK. I'm about 30 years in the industry, 10 years in consultancy, 10 years in fabrication, and around about 10 years in steel manufacture as well. So I do have the luxury of having seen the construction supply chain from a few different angles, which I think is a good thing. I'm also joined on the call this afternoon by a colleague of mine, Neil Tilley. So we kind of cover the UK together. So if ever you need some support from ArcelorMittal on kind of all matters relating to steel, then myself and Neil are a good point of contact. I'm also joined on the call by two colleagues who have helped us to set up the presentation today, and that's Justine and Pascal. And just before we kind of start, I'd like to say thank you to those three people for their support today. So I think the numbers are starting to plateau out a little bit, so we'll make a start on the presentation. Just a little bit of housekeeping before we kick off. So the first one is that there will be a QA session which will hold at the end of the webinar. But I understand that as we go through, slides might prompt questions. So I would encourage you to use the Q&A chat at the top of the screen and post your questions there. The questions might be answered as we go through the presentation. And if they are, that's fine. And if they're not, we'll pick them up at the end and we'll do our best to answer those questions. We're going to record the broadcast. And we will send you a copy of that and a copy of the slides in the coming days. So this is the rough agenda for the presentation. We've got a mixed audience today. So we have some people from ArcelorMittal who are listening in, but we also have some contractors, some architects, some engineers, some environmental consultants. And we will start off kind of looking at the steelmaking process from the point of view of giving context within a design environment. I think the one thing about tackling the climate emergency is that we all need to be quite well connected and to be able to see things from different angles so that we can integrate processes, design processes, manufacturing processes together and have a deeper knowledge of the supply chain. So we'll start off with the steelmaking processes, but it will be relevant certainly to a structural engineer and to a broader construction supply chain. And we will tackle some numbers towards the end of the presentation. So hopefully something for everybody. So starting with the climate emergency. A little bit of a timeline, not dealing with the stuff which I guess you're already aware of, but really just wanted to pick it up as it started in the UK. So for me, it kind of started back in April last year with the Extinction Rebellion demonstrations, which took place in London. And then in June of that year, Theresa May, as she left the UK government, committed the UK to being net zero carbon by 2050. And that same month, a website popped up, which was the Construction Declares website. So just in case you're not aware of that, this was about organisations, companies basically declaring or acknowledging that the building industry, the construction industry, is responsible for 40% of global CO2 emissions, and signing a declaration to say, well, you know, as a company involved in that sector, we're going to do something positive to achieve that net zero commitment by 2050. Organisations such as the Royal Institute of British Architects, organisations such as the Institution of Structural Engineers have all signed up to that declaration, but it also includes construction companies, architects, engineers, MEP professionals, cost consultants. The diversity in the UK is greater, but it has travelled globally as well. I think there are about 12 countries that have signed up to that agreement, but it tends to just be the architects in those countries. So that's kind of where we're at the moment with that. Now starting to look at design guidance that's available. There's a couple of documents which I'll mention. There's the Royal Institute of Chartered Surveyors, which have this guide here. This is all about getting the measure correct, because if you're going to start to compare one scheme with another scheme or one building with another building, you've got to be able to compare apples with apples. So that's what that guide's about. That came out in November 2017. In July of last year, there was a guide from the RIBA came out, and we'll pick up that later in the presentation. And in January of this year, there was another guide, the LETI Climate Emergency Design Guide. And again, we'll pick that up later. And then last month, we have the guide from the iStruct-E. So it's a paper which will launch the guide, which will be going out shortly. And that's been authored by John Orr, Orlando Gibbons, and Will Arnold. So that represents guidance being given to structural engineers on how to calculate embodied carbon. ArcelorMittal, we launched our climate action report, the first climate action report in May of last year. In November, that was very shortly followed with that announcement of a 30% reduction in CO2 emissions by 2030. That's the target that we're chasing. And then in June of this year, we issued our second climate action report, which builds on the first. And you'll see a little bit of a change in thinking between those two reports. So, working a little bit with that second climate action report from ArcelorMittal, what is our strategy? Well, our strategy is threefold. First of all, we're going to work within our own little bubble, and we're going to see what we can do with the steel making processes, which we currently use. And I'll take you through that in the presentation, but just in very broad terms. We then have a program called Steligence, which is kind of aimed at supporting designers to deliver on low carbon buildings, but of course using a palette of steel products. And then there's a third aspect to the strategy, which is something called responsible steel, and I'll deal with that one first. So responsible steel, what is it? It's a responsible sourcing standard. It's not ArcelorMittal's baby, if you like. We are quite heavily involved in the standard, but it's a not-for-profit organization. And it's concerned with the sustainability credentials of the steel manufacturing industry, not the fabrication industry, but the manufacturing industry. The first 7 principles in that document essentially deal with people in broad terms. So it's about looking after the people and being responsible for the people in our industry. And then the 5 principles that follow that are generally concerned with the environment. But the one that I want to draw your attention to is principle 8. And in that, if you are a member of Responsible Steel, if you have been audited to Responsible Steel, then in that audit is acknowledgement that you have committed to the goals of the Paris Agreement. So that's the connection there. I'm going to start to talk about steelmaking processes and how we're going to adapt them. But I thought it would be useful to look at the steelmaking processes and the ironmaking processes that we use today. So I'm going to start with the blast furnace, which you'll be familiar with. Many of you will be familiar with. So the blast furnace produces liquid iron. It uses primary resources, which are basically coal, limestone, and iron ore. You get liquid iron out at the bottom. The slag kind of floats on top of the iron, and that's used for a cement replacement product, as you all know. And out of the top goes the gases. That's the chemical process. So we use carbon as a reductant to separate the oxygen and the iron ore. And that's the role of the carbon in that process. So one that you're probably quite familiar with. Direct reduced iron might be not so familiar to you. It produces a solid iron product called sponge iron, and it uses natural gas as a reductant. Now, the top line of the chemical equation there is exactly the same as the blast furnace. So carbon is used to combine with the oxygen to separate the iron and the oxygen out from the ore. But you'll notice in that second expression that the hydrogen component of the gas also plays a part in that reduction process. And it's that one that's quite important in terms of the future of the steelmaking industry, because that demonstrates that we can reduce iron ore without the need for carbon. And therefore, the only thing that we emit to the atmosphere is water. So generally, once you've made iron, you then move on to steel. And the process, there's one of two processes that is used. The first one is the basic oxygen furnace, or the basic oxygen steelmaking process. And what we do is we take the liquid iron from the blast furnace, and we essentially blow oxygen through the iron, and that turns it into steel. A reaction takes place which generates a lot of heat, and the way that we control that heat is by adding scrap, and that scrap acts as a coolant charge in the process. When you pair up the basic oxygen furnace with the blast furnace in the steel industry, that's referred to as an integrated steel mill, and that kind of collection of processes is often referred to as primary steel making as well. The other process that we have is an electric arc furnace, sometimes referred to as a mini mill. And this can use basically a solid iron or a solid steel product, which you then melt down into a liquid. It's usually 100% scrap that's used, but we can use a mix of both scrap steel and sponge iron. And the thing about that particular process, sometimes referred to as secondary steel making, is that if we combine that with a green source of energy, then we can have ultra low carbon steel, and we can have that today, and that's something that we're looking at as an organization, as a company. So what we've seen kind of just in that initial introduction there is that steel is already quite a circular material. We capture all the available scrap that's globally, and that is fed back into the basic oxygen furnace, or it goes into the electric arc furnace. So all steel has recycled content. The only thing that varies is the percentage. We haven't talked about reuse, but we will talk about reuse a little bit later on in the presentation. And reuse for steel has significant potential. So moving on and talking initially just a little bit about ArcelorMittal, so you understand the company. We think of ourselves as a mining and metals company, but actually we manufacture an array of construction products. Some of those you'll be familiar with, but maybe you won't realize that we also produce reinforcement. We also produce fibers for concrete, and we also produce GGBS, which is used as a cement replacement. And we actually have a tie-up with a company called EcoSem. So we basically have an interest in construction products. We have a global presence, but what I want to do is just drill down on two items on this slide. The first one is on your right-hand side there, that CDP logo. So that's the Carbon Disclosure Project. Last year, we received an A- grade, which puts us at leadership level. And that is all about being transparent about carbon and reporting on carbon. And hopefully that transparency will be reflected in this presentation. I now want to draw your attention to the blast furnace in the middle and just talk a little bit about the bits of kit that we have as a steelmaker. So we have 51 blast furnaces, we have 33 electric arc furnaces, and we have 13 DRI plants, and they produce between them 90 million tons of crude steel. About 30% of that volume goes into the construction sector, about 30% goes into the automotive sector, and the remaining goes into other industries. Of those of that volume, the 51 blast furnaces produce around 70% of the volume, the 33 electric arc furnaces about 20%, and the 13 DRI plants about 10%. So that kind of gives you a measure of which bits of kit produce the most volume. Very quickly, just want to introduce you to some sites at ArcelorMittal. We have 2 mills in Luxembourg. One is Belval, the other is Differdange. They both use electric arc furnaces to produce the steel there, and they produce essentially 2 products, section and sheet piling. On the right-hand side are 2 EPDs. They are specific to both the products and also those mills. So one is for high star steel sections, the other is for our sheet piles. And the environmental data in those is reflected in the manufacturing process and the products. Just want to quickly mention one of our mills in northern Spain at Oliveira. Again, that's an electric arc furnace mill, and it produces section. Moving on to Gijon, again in northern Spain. This is a blast furnace facility. So blast furnace to produce iron, then a basic oxygen furnace to produce steel. And again, on the right-hand side there, we have an EPD, which is specific both to the heavy steel plates that are produced at that mill and also to that manufacturing process. And again, that is reflected in the data in that EPD. So again, this is all about transparency. The third facility I want to introduce you to is at Hamburg. So this produces direct reduced iron. And that's the image there on the bottom left-hand side there of what that product looks like as it comes out of that furnace. So as I mentioned, this still runs on fossil fuels, but it runs on gas at the moment, which is a little bit more friendly to the environment, if I can put it that way. And it produces a product called wire rod. Wire rod is a feedstock for things like bolts, but it's also a feedstock for reinforcement. So rebar that goes into concrete. And once again, on the right-hand side, we have an EPD that is particular to that mill and particular to that product. So again, transparency. With DRIs, you generally pair them up with an electric arc furnace, and that's indeed what happens at Hamburg. And at that particular electric arc furnace, we actually use a mix to produce the steel. And it's actually roughly about a 50% mix, a 50-50 mix, sorry, of direct reduced iron and scrap steel. And again, that's reflected in the EPD. The final plant that I want to mention is at in Ghent, in France. So this is what we call a strip mill. So it produces kind of coated steel, which is used in the automotive sector, but also in construction products like floor decking and cladding. And I really want to mention it because we've invested quite heavily there. It could be regarded as an energy park. The largest solar roof in Belgium, about 12 wind turbines, which are all generating energy. It's a site which is trying to lead the way within the group. We've reduced site emissions by 25% since compared to 1990 levels. We reckon we're 20% ahead of the Paris Agreement, and we've set a target of 43% reduction in CO2 emissions by 2027, and of course to be carbon neutral by 2050. Once more, just to show you an EPD there, this is for our hot dip galvanized steel with a Magnellus coating. And again, that EPD is particular to that product. So now moving on and looking at the ways in which we're going to change with the steelmaking process. We have a 3-strand strategy for this. One is we're going to work with the direct reduced iron process. Another one is called smart carbon, and I'll go through those in a little bit of detail, but not too much. And the third one is obviously we're going to see increased use of scrap steel as that becomes available in the marketplace. Initially, our focus will be on still reducing the iron with carbon. And then ultimately we will transition to hydrogen is the broad game plan to take us towards carbon neutrality by 2050. So just going through those processes in a little bit of detail, but not too much. The smart carbon route. The wonderful thing about this route is it will produce 1 ton of carbon neutral steel. But that's not all you're getting. You will also get 250 kilograms of carbon neutral cement. You will also get 200 kilograms of carbon neutral biomaterials, which can be used to make plastics. We also have the option of actually removing carbon that would normally be emitted to the atmosphere and actually making steel carbon positive. How are we doing that? This is a diagram from the Climate Action Report that I mentioned earlier. I'm not going to go through it in detail, but the point that I want to make concerns that kind of circular green process. So this is an adaptation to an existing process, but the vision is of a circular manufacturing process. So a circular manufacturing process, which kind of matches the circular nature of steel as a product. So that is the way that we're thinking as an organization. The direct reduced iron process, we should have a plant running on hydrogen by the mid-2020s. We're currently working with a company called Midrex on the design of that plant. Again, it's an adaptation to an existing plant, the Hamburg plant. And all we're doing is changing the process gas that runs through that plant. But unlike smart carbon, it's not going to produce any co-products. So there'll be no GGBS, there'll be no cement, there'll be no plastics. To achieve full carbon neutrality, we do have to generate a little bit of energy using circular carbon, and that is how we'll achieve carbon neutrality with that process. So that's just a broad overview. More detail in the Climate Action Report, and in the presentation there's a hyperlink to take you there, so you don't have to troll the internet to find that. This next slide shows an interesting bit of work by a company called HSBC, who some of you might recognize. So HSBC prepared this report. The reason behind it is they wanted to understand whether the steel industry was a good risk or a bad risk in terms of how they're dealing with the carbon agenda. And obviously the good news is that they've decided that the steel industry is indeed a good risk. So that's the first point. The second point is that this table in the center of the slide there illustrates many of the steel making and iron making processes that I've just outlined, and I'll just very quickly go through them. And it also shows their carbon intensity. So at the top of the tree we have the basic oxygen furnace fed by the blast furnace with iron. So that has high embodied carbon content. If I jump down to direct reduced iron, so this is an existing process now, and that is the embodied carbon associated with that process. And then if I jump down here to the electric arc furnace process, again, an existing process. So these are the carbon impacts now, today. If we go back to the basic oxygen furnace, if we couple that with biofuels, which is what we're going to do at Ghent, if we couple that with carbon capture and use and carbon capture and storage, again, that's what we plan to do at Ghent, then we'll get to carbon neutrality. With the with the direct reduced iron, that's basically about switching the gas from natural gas to hydrogen. That's how we'll achieve carbon neutrality there. And with the electric arc furnace, it's about tapping into a green energy supply. And that is how we'll achieve carbon neutrality with that process. So lots of positive messages, I hope you'll agree. So that's about our plans for the future. But the climate emergency is now. So what options do we have available? Well, I've already mentioned our plants in Luxembourg. So the Luxembourg cluster, as we call it, that is where we manufacture our high star steel section. So that's available in a 460 grade, and there's also higher grades on the horizon. So that is a mechanism for reducing material content where your designs are strength driven. And obviously, if you reduce material content, you reduce carbon. Each of our sites produces a sustainability report annually. This is an extract from the Luxembourg cluster. And what we see here is that 2.5 million tons of scrap steel were gathered. That cluster of mills produces around about 2 million tons of steel per annum. And that's displaced 3.3 million tons of carbon. If we drill into a little bit of detail, at the top right of this slide, we have the carbon footprint of the Luxembourg cluster. So 300 kilograms of CO2 emitted to the atmosphere relative to a ton of steel. And then that is broken down into scope 1 emissions. So that's the emissions that come from the furnaces, the scope 2 emissions due to electricity and heating, and then the scope 3 emissions there on the bottom. So some quite detailed information if you're looking for that. The next question is, well, how as a designer do you go about perhaps specifying electric arc furnace steel? And the one thing that you can't really do, and again, we'll touch on this later in the presentation, is simply just put, you know, all steel must be from an electric arc furnace. And the reason for that is that not all products are available in that manner. And it might not be relevant to do that. You need to know what's available in your market. But if it is available in your market, then this would be a way to do it. So I've taken an extract from the National Building Specification, and then I've modified one of their standard clauses. And to me, the sensible way to do it is to actually specify the mills that you want to source your steel from. And that way you can guarantee the source of electric arc furnace steel if that's what you need to do. But there are reasons why you possibly shouldn't do that, and I'll explain those in the presentation. I'm going to start to move on to design now, because if we're going to tackle the climate emergency, it basically starts with design. And maybe the first decision you make is not to build. If you don't build, then you're not going to use construction materials. If you don't use construction materials, then you're not going to generate carbon. So perhaps adaptation should be the first process. But that's not going to be an option for all buildings. So the next thing we look at is loads. For anybody who's worked in the design and build sector, particularly on things like portal frames, you'll know that the first thing that a steel designer will do is he'll look at skinning the loads right down, take them to the absolute minimum, because that impacts weight, and of course that impacts carbon too. The next one is to look at the materials, but perhaps in a holistic way. You know, what makes sense? It's about using the right material in the right place, considering the mechanical properties of the material, and matching those with the particular kind of design requirements that you have for the building. You then move on to design. It's about pushing the utilization to the limit where possible. If you go over by 1 or 2%, does it really matter? It's about looking at deflections. We use rather sophisticated 3D models these days, and sometimes we put limits in there. And if we don't just take a look at that, then sometimes we can add mass, we can add carbon where it's not really needed. Deflection isn't really a binary choice. It's a little bit of a grey area. If a beam deflects 2 or 3 millimeters more than it should, does that really matter? Can we live with it? The other area to look at is irregularity. Irregular grids tend to attract carbon. Transfers tend to attract carbon. Offsets attract carbon. They may be required. There may be no way around it. That's absolutely fine. But can they be designed out? If they can, they will save carbon without a doubt. And then the next step is to look at materials again, but this time you're revisiting your first decision and you're applying the carbon filter, you're applying the circularity filter. What can you do to deliver the best result Does it change your thinking? Do you need to go down another route? And then finally, really to emphasize a point, I think we need to become more integrated as a supply chain. That's both designers and manufacturers. As designers, engage with the supply chain. We're here to help you. We'll do whatever we can to help you understand the materials, to help you understand manufacturing processes. And we'd also ask for your support as well. We need to understand what you're trying to do so that we can be a positive player in that relationship. Moving on once more, and this time looking at something which is available to designers. So a number of years ago, we set in motion a process which would look at the way in which you put materials together in a building, and we called that Steligence. And it's a holistic approach to building design, so it looks at the big picture. Many of you will be aware that if you work on a building project, there are different players in that relationship. You've got cost consultants who are looking at the cost, of course. You've got structural engineers who might be looking at the weight of the structure. You've got the sustainability consultant concerned about the environmental aspects of the building. The architect who's maybe concerned more about the space and how that space works for his client, the flexibility of the building. And you've maybe got the contractors and the fabricators who are more concerned about the speed of construction and risk and things like that. If these disciplines don't talk to one another, if they don't share and trade information, then things may not all pull in the right direction. And Steligence acknowledges that. In particular, it acknowledges that the structure, the facade and services are things that need to talk to one another. So the disciplines need to talk to one another, and that will result in a structure which is more integrated. It also recognizes that operational and embodied impacts can't be considered separately. Again, there's an interplay between the two, so it needs to be considered as a whole. So in very simple terms, what Steligence tries to, well, what it acknowledges, what it realizes, is that the whole is greater than the sum of the parts. How does it deal with that? It deals with that through two tools, which again, some of you designers will be familiar with, but it's a full life cycle assessment, including end of life, supported by a full life cycle cost analysis. And what it tries to do is get that perfect balance between cost and carbon. Just to give you a flavour of what is happening with Steligence, so we've done 2 studies so far. We're looking at 5 building types. I'm just going to give you a quick overview of the office building study. So here's an illustration of the building, 13.6 metre span, 8-storey building, typical of an office building in Central Europe. So it may feel a little bit different to those members of the audience who are from the UK. On the left-hand side there, we have a concrete kind of option which was considered, again reflecting the Central European market, so primarily comprising of precast concrete products and a short span structure arrangement. And then on the right-hand side, we have a steel scheme which has been optimized with a suite of ArcelorMittal products, which all kind of bring something to the table in terms of both cost and also carbon. The study kind of highlighted 10 key benefits of the Steligence approach, the steel approach. Again, to a UK audience, you may have seen some of these benefits before, but if you've seen them in the past, they've come from a cost perspective only, possibly not really looked at carbon. So the subtle difference with the Steligence study is carbon as part of the considerations. I'll not go through all of the benefits. I'll maybe just quickly flick through 1 or 2 of the slides, but they're in the slide pack so you can see them. Some of them deal with cost, some of them deal with carbon, some of them deal with flexibility, but they are there. A big one is the reduction in the weight of materials that's used in a steel building. Again, something that will be familiar to some of the audience in the UK. This slide just really tries to sum the offering from ArcelorMittal up. So as an organisation, we make quite an awful lot of steel components, but not all components will deliver in terms of the carbon agenda. And what we've tried to do on the right-hand side is cluster those products which bring some to the table, and we've labelled them best-in-class products. So they will contribute to the carbon reduction of your buildings. Moving on now to the measurement of carbon within our buildings, and initially starting with something that many of you may be familiar with, so I apologise if you are. But there are two environmental standards which tend to be used when we're looking at the sustainability of a building, when we're looking to measure embodied impacts and operational impacts. There's 15978, which deals with the building itself, and there's 15804, which deals with the products that go into that building. The commonality between the two is what's going to be shown on the slide before you, and it's kind of the stages that you look at as you go through the design and life of that building. So it all starts with the product, with something called Module A, and it's all of the embodied impacts associated with getting materials out of the ground, manufacturing them at a manufacturing site, and getting them to the factory gate. So sometimes called a cradle to gate scope. The next part of that process is taking those materials from the factory gate, getting them to the construction site, and then getting those materials up in the air. So again, something called a cradle to practical completion scope, or sometimes called upfront carbon. The next part of the process is the in-use phase. It generally applies more to the energy used within the building, so it's operational. But if you are doing things like replacing cladding on a cyclical process, or you're replacing the M&E services, then that would be included in that part of the process. And almost the final process is when the building comes to end of life. How do you take those products down, and do they have any value at the end of life? So in terms of deconstructing the building, it's cradle to grave. If the products have any value at end of life, then that becomes a cradle to cradle analysis. So that's a full module A to D analysis. And just a nod to the I/E paper on this particular slide, because I borrowed it from their journal. I hope that's okay. I am a structural engineer. I now just want to turn my attention to the guidance that has appeared in the UK. So in July, we had a guide from the Royal Institute of British Architects. It has given targets to design to in terms of the embodied carbon expressed per metre squared. So we have a target in 2020 of 800 kilograms of CO2 per metre squared. In 2025, that reduces to 650. In 2030, that reduces to 500. Those reductions are aligned with the requirements of the Paris Agreement, so they're science-based targets. The other thing to note with this guide is that the whole life carbon as well. So it's module A, module B, module C. No module D included, but the guide does make reference to the RICS guide, the Royal Institute of Chartered Surveyors, which does give some guidance on module D impacts. The other guide which appeared in January of this year was the LETI guide. That's the London Energy Transformation Initiative. It follows a similar path in that it gives some embodied carbon targets, and those targets reduce as time goes forward. And again, it's aligned with the Paris Agreement. But those targets are based on a module A only assessment. So it's not quite the same as the REBA guide. They do address Module D, but in a more holistic way. So they're not actually talking about measuring a figure. What they're saying is, when we build a building today, can we incorporate materials which have reused content? And can we have a figure of 30% in our building today? Thank you very much. And in 2030, that will increase to 50%. And we also need to think about end of life in terms of how much reusable content do we have. So for buildings designed today, that's a 50% target. And for buildings designed in 2030, that's an 80% target. So it's a little bit of a different way of thinking about things. I'm going to stick with the Letty guide, and we're going to just drill down a little bit into those targets in terms of the superstructure consideration. So if you look in that guide, on the left-hand side here is an extract from that guide, and it shows a typical breakdown of embodied carbon for an office building. And we see that roughly 50% of it is concerned with the superstructure. And really what I've shown there is the superstructure targets now from the Letty guide. Just out of interest and purely for interest and just a simple observation, on the right-hand side, we have a typical cost breakdown for a multi-story office block. And just interesting to note that in terms of the superstructure, although the superstructure is responsible for half of the carbon, it only accounts for less than 10% of the cost. Maybe structural engineers should be paid on the basis of the carbon that they save. I don't know. Controversial. So you're given those targets. You maybe think, as a structural engineer, what on earth do they mean? And certainly that was my reaction. I did kind of do a little bit of a literature search, and this was one of the documents that I found. So it appeared in the Structural Engineer in October 2012, and effectively it was a full cradle-to-cradle analysis of 5 steel building types. And it also looked at concrete alternatives, as you'd expect. So I'm going to initially look at the embodied carbon in the total building. And I'm going to just focus on that office building. And the paper tells us that we have an embodied carbon, total embodied carbon of 452. And if we compare that with the Letty figures, initially it looks quite promising compared to the 600 target in 2020 and the 350 in 2030. So some work to do going forward. But you know, got a little bit of room to breathe at the moment. And then if we drill down and we look at the superstructure, the frame and floors, again for the office building, then the figure there is 219. And again, if we compare that with the Letty document, we've got a target of 300 now and 175 in 2030. So that might make you feel a little bit comfortable. It helped me, but we do need to understand that we're not comparing apples with apples here. So the exercise done in the paper was a cradle-to-cradle analysis. So it was modules A through to D, A through to D, so taking into account the end-of-life benefits, whereas the Letty guide is only looking at module A. So how do we start to make sense of that? So just picking up on that point and referring to the RICS guide. So in that RICS guide, which came out in 2017, so 5 years after the paper in the Structural Engineer, it has made an explicit request of designers, and it says if you are doing carbon assessments and you are looking at module D, you must not aggregate it, you must communicate it separately. And the I/E paper basically aggregated those values. So it didn't quite comply with the requirements of the RICS guide, but it was before its time. In that RICS guide, it also gives a minimum scope, and the minimum scope is module A. So that minimum scope is aligned with the LETI guide, or the LETI guide is aligned with that minimum scope. But the RICS guide does recognize that if you want a full picture, a complete picture, then really you should be doing a cradle to cradle analysis. Just to labour the point, the RICS guide says Module D reported separately. It does acknowledge that Module D can give you an idea of the circularity of the materials that you're dealing with. And really the question that I want to ask you is that relevant for a circular material like steel? We've already seen that in production processes now, there is quite a high recycled content in the steel that we're using. So it's already circular. And I also want to highlight just one of the difficulties that you might have as a designer, and maybe hint at an answer. So 2 EPDs which are available to you in the marketplace. You have an EPD for our High Star product, and you have an EPD for British Steel for their products. And if you look at the Module A values, the choice that you'd make would be obvious if you just looked at Module A. But the question is that a fair comparison? So we then look at Module D, and we see for the ArcelorMittal High Star steel, we have a value of 87. So it's positive, which means that it's a burden, if you like. And for the British Steel EPD, it's minus 1600. So that is a benefit. So why is that? Why such the big benefit? Well, the British Steel EPD, the source is blast furnace steel. So it's made from primary resources. At the end of life, that enters the circular steel system, the recycling system. By doing that, it displaces primary resources. So that's why you get that rather large negative benefit. And of course, to try and compare the two, what you want to do is you want to aggregate those values. So you're allowed to do that, but you just have to report it separately. And obviously, once you do that, you find out that the difference between the High Star steel, which is electric arc furnace, and the British Steel blast furnace steel, that difference is not as significant. And certainly when you start to multiply that by the volumes that might be involved, that figure actually comes down. So there'd be a natural inclination for any designers to say, right, we've got a climate emergency, let's go for electric arc furnace steel. And we fully understand that, but we think you just need to consider one or two other things. And this is the point which we're trying to make. So steel products are made using different manufacturing routes. There's no real reason why they couldn't all be produced using electric arc furnace. It's just that it doesn't make sense to do that at this stage in the game. So with Section, you have a choice. There are organizations that make electric arc furnace steel. There are organizations that make steel using the blast furnace and the basic oxygen furnace process. In the case of plate, there is no availability, not in the construction sector, for electric arc furnace plate. In the case of tubes, tubes are made via plate. The plate is made via the Boss process. Decking and cladding comes from the basic oxygen furnace. Reinforcement, you have a choice, electric arc furnace or basic oxygen furnace. So what approach should you adopt? Well, I think the first thing you've got to do is you've got to have that big picture view again. Steel is already circular, all the steels are captured, it's all recycled. The only thing that changes is the amount of recycled content. If we look at the global logistics, there's only about 30% of scrap available in the world at the moment. So we simply can't meet demand. So the sensible way forward, in our opinion, our humble opinion, is to look at your market, look at the supply chains, and if you have a choice, then maybe preferentially specify EAF. But if you don't have a choice in that market, then maybe that's not the sensible thing to do. Looking at end of life scenarios, and going to move on to some figures. If we look at concrete, These are kind of the industry statistics. About 20% of it's recycled, 75% downcycled, 5% landfill. There are then some figures for timber. It's a little bit more complex with timber. And then if we look at steel, about 88% recycled, 11% reused, 1% to landfill. So the thing with steel is that we've got a lot of knowledge about the end of life. With other materials, it's maybe not so certain. And maybe that's one of the issues. If you are going to compare materials, what's the best way to do it? You could just take a look at the embodied carbon factors and you could say, right, we'll compare steel with concrete with timber. If you do that, of course, you're going to go for timber because it's a negative number. You might follow that with concrete because that's a lower number. And then you might go to steel, but that's not the right way to do it. You need to take into account the metrics of the unit of measurement. So with steel, it's generally tons, with concrete meters cubed, with timber meters cubed. So we need to do some maths. We need to take that embodied carbon factor and we need to multiply it by a material quantity. And only once we do that will we start to actually understand what we're dealing with. Very quickly, looking at a couple of flooring solutions, and I'm going to follow the Letty guidance. So I've done the build up for a composite slab here on the top left. And we've come up with a value of 70 kilograms of carbon equivalent emissions per meter squared of floor area. We then do the same for timber and we've got minus 90. It's a no-brainer if you look at module A. If you do the whole life carbon approach, you'll add the module B if it's relevant, you'll add the module C, you'll look at the cradle to grave, and then you'll report the module D separately. But then maybe just to make sense of those figures, you'll then bundle them together. And what we find is that if we do a cradle to cradle analysis, that equation flips. So pretty important, I think, that you look at the full picture. Also, what's critical is the end of life scenarios. So what I've tried to do is the previous guidance in terms of separating that out for timber. But the main point is cradle to cradle is the thing that gives you the full picture. If we look at short span or clear span, so again, I've seen a little bit in social media talking about the fact that, you know, if you want to save carbon, you've got to go from clear span to short span. If you make it a binary choice, you can't argue with that. But I think there's a little bit more to it. So what I've done here, again, just looked at module A as required by the Letty guide. Our slab has an embodied carbon of 70. If we do a short span beam, we add 14 kilograms of CO2 per meter squared to that. If it's a long span, it's 20. So the difference is 6. Is that a big deal? But let's do the full life cycle assessment. And at the end, we find out again that the difference is modest. Clear span's about value. What else do you get for the carbon that you're actually having to pay with? You get flexible space, you get a loose fit, you get space that's adaptable, that can accommodate change of use, and therefore you've got a longer in-service life. So you're getting carbon value over the life cycle. And final slide, you'll be glad to hear, just picking up on one or two themes to do with the circular economy. And it's all about loops. The first loop is the recycling loop. With steel, it's given. If you design steel today into a building, we know with absolute certainty that it will be recovered at end of life and it will be turned back into steel products. But we've got to do better than that. Repair. Repairing steel, relatively easy. Again, that's something that isn't an issue. If you think about refurbishment for buildings, steel is often a facilitator because it's high strength, low weight. If we look at reuse, 10% of steel is reused today. Yes, there's more to do. Yes, we can do more, but we're kind of on the right track. Remanufacture, that's probably one where we need to do some work. So we don't at this stage in time take back steel sections and repurpose them and give them back to market. But we're starting to knock down some of the barriers to that. The first barrier is to do with how do we actually look at a used bit of steel and certify it so that a designer's happy to use it. And that's what that publication by the SCI tries to do there. The other thing that we're looking at is demountability. And again, this is credit to colleagues at the SCI, but in publication 428, we're looking at how we can get the benefits of composite action, but actually have a much more demountable structure. So just a couple of words to wrap up, and then we'll go on to questions and answers. So just to say thank you for listening. Steel it's a little bit of a tricky material, isn't it? It does have high embodied carbon content. We can't get away from that. That is going to change going forward with those processes that we've outlined. But you've got huge potential in terms of its circularity. So the question is, how do you balance those two parts of the equation? We don't have a full answer for you, but it does have to be part of the analysis. And perhaps it shouldn't be a binary analysis. Perhaps it needs to be a little bit more holistic. Perhaps it needs to be a little bit more future looking. And really what I wanted to do is perhaps just stop there, because I've come to the end of the presentation. Thank you very much for listening. A lot of content there. Just to say before we go into questions and answers that both myself and Neil are available if you want to talk about any of the material in the presentation in detail, and we'd be more than happy to do that, and our details are there on the screen. So if we can now go to the Q&A session, and hopefully Neil will be on the other end of the line, and if there's any questions that you've asked during the presentation, then maybe Neil can start to go through those.
Thank you, Walter. Can you hear me okay?
Yeah, coming through loud and clear.
Okay. Just we've had a few questions that have come through that I've left till the end, and some that I've answered that as we go through. The first question is a bit of an admin question, but it relates to making the presentation available after the talk.
So thank you, Neil. But the presentation, the slide set that you've just seen will be made available to you in the coming days. In that slide set, what I've tried to do is put in a lot of hyperlinks to relevant information. So when you receive that slide set, you should be able to hyperlink to the various EPDs, to the carbon report, also to the I-struct-E information as well. So hopefully that'll be a useful document to you. So thank you for that, Neil.
Thank you. We've got a pretty broad church of people listening in today. So one question is, for the benefit of people who are maybe not so familiar with the terminology you might use, could you just give us a definition of what is a section?
Right, okay, yeah, thank you, Neil. So a section is usually I or H in profile. So to a UK audience, we'd call it a universal beam or a universal column. So a column, obviously a vertical element, a beam, generally speaking, a horizontal element. To a European audience, they would know them as an IPE or an HE section, but a rolled section which has two flanges and a bit in the middle called a web.
Okay.
Is that fair enough, Neil?
Yeah, and obviously they would be rolled sections, and that would include things like parallel flange channels and angles and things like that.
It would indeed. It would indeed.
Yeah.
Thank you for clarifying.
Okay. Another question is with regard to carbon storage, and whether you have any information to hand at the moment about what ArcelorMittal's plans are for that.
Carbon storage. There are plans. There is a project called Northern Lights, and it's kind of a multi-party thing. So we are one of the partners, but there are also petrochemical partners as well. And it's about looking at, well, sorry, our role in that is actually capturing the carbon. And that's one of the projects that's taking place at our Dunkirk site. I think that goes live in the next year or two, where we'll be capturing an awful lot of carbon, and then we're joining that up through this Northern Lights project with the oil and gas industry. So essentially what we'll be doing is storing that carbon in effect, the North Sea oil basin.
We've had a commercial question, which I think I'll answer, just to give you time to get your breath, and that is there a cost difference between blast furnace steel and electric arc furnace steel? The answer to that is that both are the same, because market forces dictate the price, and there is no difference between the manufacturing routes that makes any effect on the cost of steel relative to each other. And another question is regards to high steel that you mentioned earlier, and whether the carbon content of high steel is any different to that of regular steel. I presume by regular steel we would mean an S355 type grade.
It depends what we mean by carbon, doesn't it, Neil? So if we're talking about kind of embodied carbon,
yes,
that you're using in your carbon calculations, then in terms of the 460 or the 355, there really is no significant difference. If we're talking about carbon equivalent values, which is something different to do with welding, then yes, there is a difference. But in terms of embodied carbon, no difference, no significant difference.
Mm-hmm. And then I've had a question which I'll read to you verbatim. Does the carbon number of BOF include the initial stage of iron reduction?
Now then, can I answer that question? My understanding is that the number reported on the EPD for blast furnaces and for blast furnace steel incorporates everything from the materials that are dug out the ground right to the point at which that steel leaves the factory gate. So I think the answer to that question probably has to be yes. But that is a little bit of deduction on my part. Perhaps we should come back to the person on that question.
Yeah, I've actually made that comment to them. Yeah. I've got some questions that I've only just had a chance to read, so because they've come in after the presentation. An interesting question with regards to co-products from the steel making process. Is the demand for GGBS going up?
So that's an interesting one. So I have been asked about sort of demand for GGBS. Are we seeing demand for GGBS? It's actually difficult to put your hands on some figures. I think we've probably looked at it the other way. We've looked at what we can produce. The issue with GGBS is that it's a product of the blast furnace, and so it does directly relate to the activity in the industry. So the actual amount available at any one time will actually fluctuate, and that'll be a function of how busy the construction industry is, how busy the automotive sector is. And ultimately it also links to construction demand. So I've danced around that question. The honest answer is yes, there is demand for GGBS. Yes, we have seen an increase in demand for GGBS, probably due to the fact that as power grids decarbonize, PFA becomes less readily available, and the next best solution is GGBS. But it's really anecdotal. Does that help?
I think so. Okay, I'm conscious of time and that people are very busy. So there's one question with regards to high star, and do you see chances for weight reduction compared to the use of the S355 material, and what effect that might have on total embodied carbon?
So as an organisation, we've done various exercises looking at both cost and carbon, actually, by substituting 355 steel with 460. The first step in that process is it has to be strength driven. So if your design isn't strength driven, there's no reason to go to a higher grade steel, and therefore you wouldn't see a reduction in carbon. So if your design is inertia driven, for instance, there will be no benefit in using 460 grade steel. There would be a benefit in using high star because it's electric arc furnace compared to other sections, but not in terms of its strength requirements. So high star is generally good in situations such as multi-story buildings where you have high column loads. It's good for transfer structures where maybe you're looking at a truss member which is heavily loaded and you're trying to reduce the size of the sections. Yeah, is there anything else you would want to add to that, Neil?
No, I think you've covered it there. You mentioned earlier about supply chains to countries. We've had a question that's specific to the UK, but it talks about availability of electric arc furnace steel in the UK.
We generally sort of send product to the UK from our plants by boat. So it tends to come from Luxembourg, down the Rhine, and then across the Channel, or it tends to come from northern Spain, Iberia. So they are the two main sites of section, that is, into the UK. And we have round about 2 boats arrive at the docks in Immingham each week, and on each of those boats will be around about 2,000 tonnes. So you've got probably about 3,000 to 4,000 tonnes coming into the country each week. That will all be electric arc furnace steel. It will either go direct to the customer or it will be held in stock at our distribution warehouse in Scunthorpe. And at Scunthorpe we have a stock of about 30,000 tonnes at any one time. So availability should not be an issue, really.
And I'll make these the final 2 questions. We have had some others, but if you have asked a question and I haven't answered directly, it's basically because we've even given you part of an answer to your question, but we will answer your questions direct to you after the event. One relates to the details you showed about the circularity of steel, and possibly just to give a little bit more explanation of what's included in the Steel Construction Institute guides. It talks about what would you have as a classification of the steel that you might reuse from a building? I think it relates to the protocols that the FCI have, or the answer is the protocols that the FCI has produced about the veracity of the steel you take from one building, and what do you take into account when you design that for another building? Yeah,
so the FCI guide essentially looks at 3 kind of possibilities. The first one is where you have information, so that might be held in a BIM model, so it's a little bit looking towards the future, where you have test certs available, where you have section sizes available, where you have chemistries available as part of the normal construction processes today. So in other words, you have full visibility of where that steel's come from. So in that case, that steel can be CE marked in the way that any other piece of steel would be on the market, and then as a designer you have the full information that you need for that piece of steel. Now we'll get a little bit of vague from this point on. If you have an older piece of steel, it might be a case of that you have to make some conservative assumptions about strength. It may be that you have to do some limited testing to demonstrate the capacity of that member, but it is covered in that guide. I can't really go into more detail than that because I need to have a thorough read of that guide. But the important point is that it does actually cover all of the questions that you would have as a structural engineer in terms of a protocol for dealing with reused material or repurposed material.
Okay, well, we'll make this the final question. It's just asking about EPDs and their relevance, and what their relevance might be looking into the future.
Okay, interesting question. So the relevance of the EPD is it's almost like a health check, isn't it, for the steel? So it gives you that traceability. It gives you everything you want to know about the broad sustainability set. So it's not just about carbon. But obviously going forward, as we decarbonize, that data set is going to change. It's going to be slightly fluid. Initially, there probably won't be too much in the way of change, but certainly as we approach 2030 as an organization, I'd expect to see that reflected in those data sets. And then obviously as we accelerate towards 2050, then in terms of embodied carbon content, then those figures are going to be coming down as we decarbonize. So I think that's what the question was hinting at. So yes, you'd expect a change in the data sets, particularly for carbon. But remember that EPDs aren't just about carbon, they're about the broader sustainability set as well.
Okay, as I said, we'll answer questions that we have remaining as we go forward.
Could I just chip in with one comment, Neil, which I may have forgot to mention on one of the slides, and it was where I compared a composite deck with a CLT, a cross-laminated timber slab. I didn't really explain why there was a huge negative figure for the timber. And the reason why that negative figure for the timber was there is because it allowed for something called timber sequestration. So in other words, the fact that you chop down a tree, you stick it inside a building, so that carbon becomes locked away. But as soon as that tree comes out of the building to be something else, that carbon comes back into circulation. So that was why you saw that significant flip in the numbers towards the end. So the key thing there is just be careful with your data sets, understand the data sets, and if you want the whole picture, you need to do the full cradle to cradle analysis.
Okay,
so thank
just
you.
remains for me to say thank you, Walter. Excellent presentation. And we can obviously keep a dialogue ongoing after this. You have the contact details for Walter and myself, and we'll only be too pleased to pick up questions at a later date if that suits you.
Wonderful. So just one final thank you from me. So thank you to Neil, thank you to Justine, thank you to Pascal, and thank you to all those participants that listened in. Really grateful for your company for the last hour. Thank you.